So we have Professor Raghavendra Gupta from IIT Guwahati, and today he'll be taking a session on multiphase flow. And thereafter, our team member, Mr. Biraj Khadka, will take you forward with a hands-on session. So all of you have joined timely, and I would like to have an ice-breaking session with Professor Raghavendra. Sir, if you want to introduce yourself and go forward and ask them to raise some query regarding this topic, and just an informal interaction before we formally start the session.
Thank you, Payal. So I wanted to know a few things. One is that you can type or you can tell about the audience what background they are, mostly undergraduate or mostly postgraduate students. They have any prior background in CFD, and what all you have learned in. So maybe one of the attendees, they can unmute and tell what they have learned in last few days. I think it started on 19th, right?
Yes. So, sir, we have mostly students, and we also have some faculty members and people from corporate background as well. But most of them are students, and they are from they're learning CFD.
Yeah, okay. So here is a question from Arpit that what research topics you are currently working on, and he says that he has worked before on fluidized bed modeling. So yeah, I am working on primarily two aspects. My whole research is about transport processes. I am a chemical engineer by training as an undergraduate. Then I did my master's in aerospace engineering from Indian Institute of Science, where I worked a bit, learned a bit about rocket engines, etc., and then worked on modeling CFD in liquid rocket engines. And then I worked for 2 years in TCS as a CFD engineer. And post TCS, I joined for PhD in the University of Sydney, again in the Department of Chemical Engineering, where I worked on multi-phase flow modeling in microfluidics applications. So that's where I started learning volume of fluid method. Currently, we have typically two themes that understanding transport processes in. So when I say transport processes, we are looking at transport of momentum, which is say fluid flow, and transport of heat, which can be heat transfer, and then mass transfer. So we are looking at these aspects, and eventually we might also look at reactions and in different applications. So two main applications that we have as our targets. One is in chemical processing industry, so chemical reactors or separators or heat exchangers and so on. The other application that we are looking at is biomedical application. So where we are looking at modeling blood flow. So we are actually collaborating with some doctors and getting CT scan data from there. We are using those CT scan data to convert it CT scan into three-dimensional geometries and then understand blood flow in these geometries. Eventually, we would like to see that how this can be useful for the clinicians, for the doctors, for the cardiologists, or neurosurgeons for that matter. Yeah. So there are some more messages. So one is from somebody says that Nikita is also an aerospace engineer, so wants to pursue a career in CFD. And Ali is saying that he works on high-speed flow, and it was mostly gas flow. I would like to be more exposed for the applications of multi-phase flow in supersonic and hypersonic flow. So I don't actually have that application. Most of the, or almost everything that I have done on multi-phase flow is on incompressible flows. Having said that, the basic building blocks remain same, but some of the differences, for example, density not being constant, the numerical methods change, and we need to take care of the facts that the temperatures can be very high. So we need to solve all the equations. We need to have the density and that makes things complicated. So there are some people. So one I know is Professor Ratnesh Shukla at Indian Institute of Science in Department of Mechanical Engineering, who works on multi-phase flow in high-speed flows, or where the flow is compressible. So what we will be talking about today is interface capturing methods. So before we talk about interface capturing methods or multi-phase flow modeling, let me give you some background about what are multi-phase flows. So all of us have seen bubbles, droplets, etc. in surrounding us. There are raindrops. There are, when we use inhalers, there are solid particles in gas flow. When we boil tea, then there is liquid and the bubbles rising into it. So multi-phase flow is ubiquitous. It's around us everywhere. So I have had some examples here. So just to give you some motivation that where are the applications. So rising bubble, we already see in number of places. Here is an example from inkjet printer, which we all of us use for printing and also for 3D printing applications, right? Now, this is an image where inkjet printing, the droplet is printing. So when you are printing, there are a number of droplets that are being released at different time instants. And these droplets, they also need to be deposited on the paper. The droplets which are following this droplet, they should not merge with it. The droplet which are deposited, they should dry. So the entire process is very complex, and you have number of physical phenomena going on there. It has to be very precise. So modeling the process helps one design such systems, right? The other application you see here is somebody has developed a model of the dry powder inhaler. So this is a dry powder inhaler from which the drug, along with carriers, it is being deposited in the lungs. So this geometry is what represent lungs and their bifurcation. So this is trachea, which is the windpipe from our throat, and then it bifurcates into smaller pipes and so on, which we call bronchi, primary bronchi and secondary bronchi, and so on. So this essentially is a model that where when the drug is released, where does it get deposited in the lungs, because it is important that the drug is deposited where it should be, right? So that is another application, biomedical application. The third image you see here is this is a fluidized bed reactor. So you might see here a glass column in the middle where my mouse is. And in this column, there is this gray color you see is the solid bed of particle. You can imagine it to be catalyst particle, or if you want to relate with what you know, so you can say that this is a bed of sand particles. And if you introduce the gas from the bottom, then what will happen if there is nothing to stop these particles at the top? Then as you keep increasing the gas flow rate, these particles or solid bed of particles will fluidize. So you will have a gas phase in which solids are flowing. So that brings us to then we can have another set of reactors, which is called bubble column reactor. So bubble column reactor is a workhorse in the chemical industry. And why I have introduced here, because it is a very simple structure and anybody can imagine it. You have a column here, and in this column, there is the blue color represents the liquid, and through a sparger, gas is introduced. So you have a pipe from where the gas is coming, and then by some means you are distributing the gas at different points. It might be a plate, it might be different holes in pipes, etc., or in a ring pipe, so which is called sparger. From this, you are introducing the gas. Depending on the gas flow rate, you can have a number of bubbles. The idea here is that when one needs to do gas liquid reactions, it might be in the pharmaceutical industry or chemical processing industry. So this configuration provide the large interfacial area, large area between the two phases, gas and liquid phases, which is where the reaction is going to happen between the two phases, gas and liquid. In this system, there will be number of bubbles, millions and millions of bubbles. So if we want to model this, the details which are present in this system are enormous. If you look at the system and the entire reactor, then you have a reactor scale where millions of bubbles are present. Now, if we focus on a small collection of bubbles and the liquid surrounding it, which we call, say, a mesoscale bubble swarm, so a collection of bubbles, then what you need to take into account is bubble and bubble liquid interaction, because these bubbles will coalesce, they will again break up. More than two bubbles may coalesce. So this bubble and bubble liquid interaction needs to be modeled. When they are coalescing and breaking, that part needs to be modeled. Now, if you further zoom into, then you have, say, what is called micro bubble scale. So if you just focus on a single bubble, then you are looking at motion of a single bubble, what we saw on the previous slide. So then you are looking at the relative motion between bubble and the surrounding liquid. So if you remember, all of us in fluid mechanics course, we have studied about a drag on a rising bubble and so on, right? But this rising bubble is not always spherical. It may deform. What is the drag that it experiences? What is the lift that it experiences? What is the flow field behind the bubbles, which we call wake, and how the vortex shedding occurs, and so on. Now, the physics also changes. If there are impurities in the system, then this bubble may act as a hard sphere because there is no interaction between the gas inside and the liquid outside. It becomes a hardened surface. So there are a number of issues. The point I want to bring home is that for in this a typical multi-phase system has number of scales. You need to resolve the details at multiple scales. For example, in this case, the flow around a single bubble and understand the flow physics around a bubble. Then you understand what is happening between two bubbles and bubble liquid interaction, coalescence of different bubbles. So bubble interaction and bubble liquid interaction put together, and their interaction will also involve coalescence. Now, all this put together, when you introduce or when you look at the reactor, ultimately, as an engineer, you would like to understand the performance of this reactor. So a chemical engineer, for example, may want to know what is the rate of reaction in this reactor, what is the yield or what is the conversion that I am going to get. For that conversion, what he needs is he needs the bubble size distribution. From the bubble size distribution means how many bubbles of what size are present, so that I know the interfacial area and I can use that interfacial area in my reactor model. Right. Now, so that gives me the reactor performance. Now, the other issue here at the reactor scale is flow regime. So in most of the multi-phase flow systems, you get different flow regimes or flow patterns, which refers to the arrangement of phases. So for a bubble column reactor, what you see here is there are different flow regimes. In the first is perfect bubbly flow. So So if you have smaller bubbles which are of uniform size, then these bubbles are distributed everywhere homogeneously, then you call it perfect bubbly flow, smaller bubbles. If you further increase the gas flow rate, then what you will have is the bubbles will start coalescing. Some bubbles will coalesce and then they make bigger bubbles. So in this, you will have small bubbles and bigger bubbles. So it is imperfect or bad bubbly flow. And then you have, if you further increase, then these smaller bubbles will further coalesce and make bigger bubbles. So there's a lot of unsteadiness or a lot of transient behavior in the system. This is called churn turbulent. And in this case, where the bubbles have grown to the size of the column itself, which is called slug flow. Because ultimately in this system, we want the system to be stable. We want large interfacial area. Large interfacial area, we know from geometry, will be when these bubbles are of a smaller size, right? So one needs to know that at what gas flow rates we will get what flow regime, and then you can model it accordingly, right? So if we define multi-phase flows, they are complex and they involve interaction between different entities. Multi-phase means they can be more than one phase. It can be, say, gas and liquid phase. It can be liquid and liquid phase where these phases are immiscible. So, for example, oil and water can be a multi-phase flow. And there can be gas and solid flow, there can be liquid and solid flow, or there can be gas, solid, liquid flow, or gas and liquid, or more than two liquids. So there can be different combinations. Typically, what you will have that one phase will be continuous and another phase will be dispersed into it. So you will have, say, for example, in the bubble column reactor, there was a continuous stream of or continuous liquid phase, and in that you have gas bubbles dispersed into it. So gas is the dispersed phase in the bubble column reactor, and the column is the continuous phase. Then you will have interaction between dispersed phases. So you will have interaction between bubbles. Now, most of these systems that we use in chemical engineering applications or in any application, for example, in industry, conventional industry, the flow is turbulent. And the turbulence you might have studied or you might have heard about it in few previous lectures, if I am correct. Then apart from the single phase turbulence factors, you need to also take into account how does particles and their motion. When I say particle, it might be solid particle, or it might be bubbles, or it might be droplets. How do they affect turbulence and how the turbulence affect them? So the two-way interaction of turbulence and particle, that will need to be taken into account in your models. The particle shape, most of the models that we have as of now, they assume the particle shape to be spherical, or they use the correlation which have been developed for spherical particles with a correction factor for the shape. So that is irregular particle shape. It may have the particle size will not be same. So one need to know the particle size distribution. And then, as I showed you in the previous slide, there are different flow regimes, homogeneous bubbly flow or the bad bubbly, where you have a smaller and bigger bubbles, churn flow and slug flow. So depending on the flow regime, your modeling strategy will change. So the transition between flow regime is another challenge that needs to be modeled, because it might be difficult to use a same single approach to model all the flow regimes. And when you need to go from one flow regime to another, you need to be carefully weighing your options, what method to use. And then apart from that, you have multiple length and time scales. The bubbles might be generating in a matter of, say, a few microseconds. And the bubble size and the reactor size both are important. So that means in modeling perspective that your time scale or your time step size should be very, very small, of the order of sometimes of the order of 1 microsecond. And the mesh size or the grid that you use, the grid size may be required that you have 15 to 20 grid size across the bubble if you want to resolve the bubble in your model. So the computational requirement for your system might be very large if you want to capture all the length scales. And then on top of that, the flow is not always very calm. It has instabilities. So instability is a typical example is you have seen the waves on the sea. There are a number of waves, and then those waves keep breaking. So the interface is disturbed, and this gives rise to different instability. Say, for example, Kelvin-Helmholtz instability or Taylor instability, and so on. Right. So let us look at, so this gives you probably a background that what multiphase flows are and what are the challenges when you model multiphase flow. So let us look at a two-phase flow system. And when I say two-phase flow, I am talking about fluid phases. So it might be a gas-liquid system or liquid-liquid system. So if you model this two-phase flow, what are the general equations? Now, let us assume that the flow is continuum. Only then we can write the partial differential equations, because everything, the first assumption that we make in fluid mechanics is the fluid is continuum. Then the flow is incompressible, and we will see those equations for Newtonian fluid, but those things can be taken care. Now, for simplicity, we will also assume that there is no phase change. The fluids are immiscible. So mass conservation equation, you see that this is the regular mass conservation equation, except that we have a subscript k in density and velocity vector. So the bold here represents the vector, right? Similarly, the momentum conservation equation, it is our very familiar Navier-Stokes equation. You might have seen it almost in every lecture by now. So here F is the body force term, mu is viscosity, rho is density, and K. So this also looks familiar. The only thing is that you will have to write mass and momentum conservation equation for each phase, right? Now, the next thing comes boundary conditions. So we are not talking about a particular system. When it comes to a particular system, we will see what is the flow at the inlet, etc. But one boundary that we have inherently present in our multi-phase system is the interface between the two phases. So for example, if I talk about gas-liquid system, where the gas is dispersed in bubble column reactor, you have a bubble. Then at the interface, so if I say that the blue represents the liquid and yellow represents the gas phase, then let us say there is velocity field associated with gas as V1 and velocity V2. So this interface, we all know that this interface is very sharp, very thin, and it is defined as boundary, which separates the two phases. Now, it is only few molecules thick in reality, right? The boundary condition, first boundary condition we employ at the interface is that the velocity is continuous. The velocity component normal to the interface. So if there is no phase change, then the velocity with which the gas is moving normal to the interface, with the same velocity the liquid needs to move. So the velocity normal to the interface will have to be equal. Otherwise, what will happen? Because if they are not equal, that means there will be some void, which cannot be, right? Or there might be something needs to be compressed. So it might change when we are talking about compressible flows, but for incompressible flow, this boundary condition needs to be satisfied. Now, the other condition is that the velocity which is tangential to it, the velocity tangential means velocity along the interface. at each point it might be different, right? So the velocity component tangential to it, they also need to be equal. That will be that if the surface tension is constant. If the surface tension is not constant, then something called Marangoni stress will come into picture, which we are not talking about. So if surface tension is constant, then the velocity tangential to the interface will also need to be constant. So that means if the velocity normal to the interface, they need to be same in at this point. On this side, velocity normal to the interface, that side they are equal. The tangential velocity on both sides of the interface are equal. By both sides mean just next to the interface, right? That is the boundary condition. So that means the velocity, entire velocity, tangential and normal component, if they are equal, then the velocity vector, they need to be equal. So velocity continuity is first condition which comes from our kinematic, or which we call kinematic condition, because there is no force that we have talked about. So let us talk about the other condition, which is dynamic condition, where dynamic refers to when we also take into account the forces that the fluid experiences. So in our system, we have two kind of stresses, normal stress and viscous stresses. Like we had normal component of velocity and tangential component of velocity. So along the direction normal to the interface, you remember normal to the interface, or right? So if the pressure normal to the interface, you will have viscous normal stress or pressure. So when we read about Young-Laplace law, what is the pressure difference inside the bubble and outside the bubble, or you might have done the problem of pressure difference across the soap bubble, 2 sigma by r, and so on. So that is the pressure difference between inside and outside. That was for a stationary bubble. But so what we have here is pressure difference plus n dot tau 1 minus tau 2 is nothing but if there are viscous normal stresses, then they are also taken into account. So the difference of normal stress is equal to sigma kappa. Kappa is curvature. So curvature of the interface for a bubble, it will be 2 by r. So if you write this 2 sigma by r, then basically for a stationary bubbles in a liquid, you will have this delta P is equal to 2 sigma by r, which we call, or which we all know as Young-Laplace equation, right? So that is our boundary condition for the interface. Now, in the direction tangential to the interface, again, we will have this, which is where sigma is surface tension. Now you have a gradient of surface tension. So if we say that there is no gradient of surface tension, then this is 0. So then tau 1 is equal to tau 2. That means the tangential stress needs to be equal. N cross tau 1 will give you the tangential stress. So the tangential stress on this side and on that side, they will be equal. If you have my surface tension gradient present, then that will be different. So we will not talk about those to simplify things. Okay, so we have talked about the kinematic condition, which says that the velocity should be continuous across the interface. Dynamic condition, which says that the tangential stress should be equal on both sides, and the normal stress should be balanced by surface tension, or delta P is equal to sigma kappa. Now, so those were the general equation for two-phase fluid flow. Now, depending on the system you are studying, there can be different approaches that one can use. So one approach is where interface can be resolved. And the other is where interface, it may not be possible to resolve the interface. So let us take some example. We were talking about a droplet being released from a printer, right? So we had this printer nozzle head, and from there a droplet is being released. So this droplet is coming, and then surrounding there is air all around. and we will need to know what is the shape of this droplet, how does it go and deposit on the paper maybe. So all those things needs you to capture the interface between the phases. So here, that's what it means, that interface needs to be resolved because we have only one droplet and another droplet coming at another time. Now think about a rising bubble problem, the very first image or very first video that I had in my slide. So again, that rising bubble, there is only one bubble and you have to model the motion of this bubble. Fine. You can model the interface. You can capture the interface. But if you need to model flow in the entire bubble column reactor where there are millions of bubbles, now it becomes difficult to model all those bubbles because the condition in these systems is that when you are resolving the interface, you need at least 10, 10, 10. Let us say generally you need 20, 20, 20 or 15, 15, 15 cells across the bubble. So you need 10 grids across this side, 10 grids across this side, 10 grids across this side. So that means 10 raised to the power 3 number of elements for one bubble. Now, if you want to model 1 million bubbles, motion of 1 million bubbles, and these bubbles are moving dynamically, so you want your mesh to be refined everywhere, then how many elements you will need? 10 raised to the power 6 into 10 raised to the power 3 to resolve these many bubbles. And then apart from this, you will need the space which is there in the liquid. So you need at least 10 raised to the power 9 number of elements, which is considering even today's computational power, you need enormous amount of computing power, enormous amount of time, and these simulations are not steady state. You need to model it over a long period of time. The time step which will be involved will be of the order of 10 raised to the power -6 or 1 microsecond. So you will need to simulate this, say 10 raised to the power 6 time steps only to understand the flow behavior in 1 second, right? So in such cases where the number of bubbles are large, then we do not, or we give up on this ambition that we will resolve the interface. What we use is averaged equation. So in those average equation, we can use Euler-Euler approach, where there are two phases, two fluid phases, or Euler-Lagrangian approach. Euler-Lagrangian approach is more useful when your bubbles or solid particles are involved and their concentration is low. Or the more advanced version of Euler-Lagrangian is what is called, say, CFD-DEM approach. So those approaches will be discussed by Professor Naren, if I remember correctly, in tomorrow's lecture. And what I will be focusing on today is on the volume of fluid method. So there are different interface capturing methods where you can capture the interface or you can resolve the interface, model this flow. Some of those I have listed: volume of fluid, or popularly known as VOF. You can use interform solver in OpenFOAM to model volume of fluid method. Then you have level set method, phase field method, marker points method. And then there is entirely different approach to model fluid flow, which is not using Navier-Stokes, but that can also be used to model multiphase flows, which we call Lattice-Boltzmann Amici-Steel method. Right. So we will be talking about, in general, the approach in all of these. And then we briefly talk about what does VOF take and what is involved in level set method. So let us look at the equations again. These are the equations that we talked about, and these are the boundary conditions that we talked about. So these methods are also called DNS. You might have heard of DNS in a different perspective, or in a different parlance when people talk about turbulent flow. Then DNS is a popular term which is called direct numerical simulation, because you want to model turbulent flows, you need to capture all the time and length scales, the phenomena that are happening at the smallest possible scale of time and length. So if you can do that, then that is what is called direct numerical simulation, and you don't model anything heuristically or empirically. Now here because we are capturing the interface, we are not using any model, so to say, which is empirical in nature. Everything is coming from first principle. So these methods, volume of fluid or interface capturing, interface tracking methods, they are also called DNS methods. Okay. Now, you might see two terms very interchangeably used: interface capturing and interface tracking. So if you have an interface, there can be that if you have a grid. So some methods, for example, VOF, might tell you that what is my volume fraction. It might tell you that there is the volume fraction in this cell is 0.5, volume fraction in this cell is 0.9, and volume fraction in this cell is, say, 0.1, something like that. But it will not tell you that this is what my interface is. Okay. So you need to construct the interface in this. So such methods are called interface capturing method. Another method might be that you have an interface and you are seeing that how this interface is being tracked. So at this point of time, interface is here. At this point of time, interface is here. So that is called interface tracking method. So in the interface tracking method, you have an interface and you are tracking. Interface capturing method, you construct an interface by the volume fraction field that you have. Okay. Now, in both the methods, as you might see that when you talk about, say, interface, I have in this, if I have a function which let us say, call it alpha, then this alpha is, say, 1 in this phase and 0 in this phase. Then I call it a marker function, that one value is associated with phase 1 and another value is associated with phase 2. So it might be 1 and 0, it might be 1 and 0 eventually also represents the volume fraction. So if I am talking about gas liquid system here, this 1 represents the gas and 0 represents the liquid. It is volume fraction, right? Now, it might be also that in one phase I say that the value is positive, in another phase the value is negative, and so on. So, but there is some kind of marker function that is used, and then we use an advection equation. So advection that means this marker function, how this is flowing along with our flow. So it's kind of tracer. How does this tracer flow or this tracer field flow in our system with the velocity field? Now, so interface they can be 2D or 3D depending on what kind of simulations that we are talking about. A very common example of interface can be that if you have an annular flow. So annular flow is that you have a pipe, and in the pipe you have a gas liquid system. So if the liquid is flowing, if you have a very large velocity of gas, then what will happen? That the liquid will be on the wall, there will be a thin film of liquid on the wall, and then there will be gas phase in the core. So this is an annular arrangement where there is a liquid flowing in annulus. It might be in gas liquid system or it might be in liquid systems. So in such cases, you can have a smooth interface flow. You can have bubbles flowing through the systems or gas liquid systems. So you can have thin films. Now, these interfaces needs to be modeled or need to be captured, and their motion needs to be captured. So as I said, that we will have a marker function. This marker function can be 1 in fluid 1 and 0 in fluid 2. How the motion of this marker function will be del C over del T plus V dot del C is equal to 0, where V is the velocity field. If you remember, del over del T plus V over C, all this is what is material derivative, which represents that how C is traveling with time. So this material derivative of C is equal to 0, that represents the motion of C. So there is a marker function and the motion of this marker function. Now we have, so marker function tells me that in this region, at this point in time and space, I have C is equal to 1 or C is equal to 0. So that tells me if it is gas or liquid. Now what I could do, I also will need the normal to the interface and curvature of the interface, as we will see as we go along. So normal to the interface can be modeled by grad C. So grad C is the marker function. So grad C will give you a vector normal to the interface, and if we simply divide it by its magnitude, then you will get a unit vector. So which is the unit vector normal to the interface, which we will require, say, for example, to define the interface direction or define the normal to the interface. We will also need the curvature of the interface, because when we talk about surface tension, we will need sigma kappa. So kappa is defined by del dot sigma. Simple geometry, it comes from there. So we will not go into those details, but the curvature of a curve or surface is del dot n. Okay. So we can use or we can remember these relationships. Now what is done in these interface capturing methods, that one uses a single fluid formalism or one fluid approach, which means then that even though you are modeling flow of two phases together, you solve only one set of conservation equations. So if it is isothermal incompressible flow, then you are solving one mass conservation equation and one momentum conservation equation. So let us look at what is different in this. This appears to be very similar. These terms also appear very similar to our familiar single phase Navier-Stokes equation. This was there, this was there, this is our body force. This is a different force which has come in this. So we will talk about this FSB. Let us remember that. The other doubt you might have, or you might ask yourself, that this is a two-phase system. So I have gas and liquid. Now what rho I will use here and what mu I will use here, right? So because there are two phases, gas and liquid, and mu is viscosity. So which viscosity, which gas? So now the answer is already there, because we have already talked about that there is a marker function or indicator function which marks or indicates that I am in the gas phase or I am in the liquid phase. So if C is equal to 1, I am in phase 1, C is equal to 2, I am in phase 2. Now, if I am in phase 1, I will use rho is equal to rho 1. If I am in phase 2, I will use rho is equal to rho 2. So the next question will be, what if I am at the interface? So what we could do is we can write these at volume fraction weighted average. So rho is equal to rho 1 alpha 1 plus rho 2 alpha 2, and mu is equal to mu 1 alpha 1 plus mu 2 alpha 2. Remember that alpha 1 plus alpha 2 is equal to 1 if you are using say 1 and 0 concept, right? Where 1 and 0 also represents the volume fraction. So this gives you volume fraction weighted average will give you. Now, if you are in phase 1 where alpha 1 is equal to 1 and alpha 2 is equal to 0, then you will effectively have in phase 1 rho is equal to rho 1, because alpha 1 is equal to 1 and alpha 2 is equal to 0. Similarly, mu is equal to mu 1. On the other hand, if you are in phase 2, rho is equal to rho 2. Now, if you are at the interface where maybe alpha 1 is equal to 0.5 and alpha 2 is equal to 0.5, then you have rho is equal to rho 1 plus rho 2 divided by 2, right? So you have those relationships for mu and rho. Now, let us go back to those equations. So the challenges in these equations is that you need a marker function, because you need alpha and rho. So we have already talked about how the marker function is, how you can define initially that this is my marker function, and then it has to be found, or it has to be calculated. So for calculation, you need an equation. So we already talked about that there is an equation, advection of a marker function del C over del T plus V dot del C, or V dot grad C H. We can use it. Now, the marker function take different values in different fluids. It must be updated to take into account this interface. So that is this marker function business we have already talked about. Now, the next question is that how do we model surface forces? Surface tension was the another problem, because we are talking about that we have solved only one single set of equations, and we had one force. The boundary conditions were that the velocity is continuous. Now, even if you are solving single phase, the velocity is continuous, shear stress is continuous. So the boundary conditions of velocity continuity or velocity is continuous at the interface is taken care of, because it is modeled as single phase. Shear stress is continuous, that is also taken care of because you are modeling at single phase. But there is a jump in the normal stress, and that is equal to surface force or surface tension. And this surface force is only non-zero at the interface. Everywhere else, there is no surface tension. So how will we incorporate it? We will add this in our system of equation as a body force. This is what this surface force was, FSV, or surface force approximated as a volume force. And there is a model proposed by Brackbill et al., which is called continuum surface force model. So you are modeling this discontinuity in the surface force in the continuum system of equations. If you look at the system of equations, they are all terms are force per unit volume. So you model it the sigma kappa, which will be your delta P, or it will be unit of racers. And then you are saying that this is the direction. What is the direction? Unit normal. Remember that we have already talked about how to model grad this unit normal, grad of C over mod of grad C. And what is this delta? Delta is Kronecker delta function, which is non-zero only at the interface. So this is your interface. It is zero everywhere and non-zero only at the interface. So that means this force will be zero everywhere, only at the interface it will be non-zero. So one can also calculate this, or one can write this in terms of C. So if you write this in C value, the grad C, if you look at grad C, what is grad C? The gradient of marker function. The marker function on this side will be, say, 0. On this side, it will be 1. So gradients will be 0 here. Gradients will be 0 here. Only here, it will be non-zero. So you can model this FSV in terms of C and grad C, right? So we have got the expression for surface force model. Now, this we can use different approaches or different methods. And what is different in different methods is the marker function we use. So in volume of fluid method, we use what we have been talking about, that the volume fraction is the marker function. So it will be 1 in phase 1 and 0 in phase 2, which is the volume fraction of phase 1. Okay. Then there are in level set method, we use a level set function, and we will not be talking about phase field method. So the volume of fluid method, the advantage is that because you are writing the conservation of, or you are writing the volume fraction advection equation, which is also conservation of one phase. So mass of phase is inherently conserved. So that is a good news here. But the problem here is that the cell is diffused over few cells. So your interface, the interface is diffused over few cells. So your interface is typically sharp. Physically, it should be very sharp. But this is a discontinuity which will be modeled as diffused over few cells. So you need to use some special treatments to make sure that your interface remains sharp. So in OpenFOAM, there are different techniques that have been developed and different softwares uses different methods. So this is not interface reconstruction. By mistake, it is there. In OpenFOAM, what is used is a compression term. So this is your volume fraction advection, where alpha is volume fraction of phase. And there is another term which comes from purely numerical considerations. If you look at this equation or this term, if alpha is 0, then this term is 0. If alpha is equal to 1, this term is 0. This term will be there only at the interface. Okay. And this VR is the relative velocity, which comes numerically using this formula. C alpha is something which gives you control over it. If you substitute C alpha is equal to 0, then this term will become 0. Then you are not using compression. Otherwise, if you use C alpha is equal to 1, you will have a typical or the conservative compression. Otherwise, you can use the higher values, say 2, 3, up to 4, you can use the value of C alpha, so this is to keep your interface sharp. It is not diffused. It might not look a very diffused interface. Now, there are implications of it, which I don't think that there is time to discuss this. Another method is that one can, depending on the volume fraction. So this is an image from Hart and Nicholas 1982 paper, where the interface is the one here. The hatched area represents one phase and the white area represents another phase. Now, what they suggest that one can approximate the interface by lines. So this is what is called SLIC, or straight line interface reconstruction, where they represent the interface in a cell based on the volume fractions and surrounding volume fractions. Then there was a improvement over it, which was called by Young's piecewise linear interface reconstruction. So in place of the lines parallel to the cells, which is a rectangular or square cell arrangement, one can have the interface reconstruction, which is represented by lines. But the problem or the issue here also is that these lines are not necessarily connected, as you can see here and here and here. But this is a very popular technique which people use. Then there are methods where people have used level set method and volume of fluid method combined. Right. So another problem with volume of fluid method, which one needs to take care, is what is called spurious currents, because you are modeling. So this is a simulation of a droplet, which is represented by this red color. Okay. So this is simulation that a droplet is in a liquid which is stationary. So neither the droplet is moving nor the liquid is moving, and there is no gravity. So the physics suggests that this droplet should remain stationary in this. There should not be any velocity field. Everywhere the velocity should be 0. Now there will be pressure jump across the interface. Depending on how well we model the pressure jump, it should be 0. But the problem comes in the calculation of the kappa, which is surface tension. So sometimes, or in many cases, in implementation of volume of fluid method, one sees these velocity vectors, as you see here, these recirculations or oscillations around the interface. There will be oscillations in pressure as well as the velocity field. And these are called spurious or parasitic currents, which are associated with volume of fluid method. So one of the effort that one needs to make, or one need to be careful about that these spurious currents are minimized. Now, just 2 minutes, I will briefly describe what is level set function. Level set function, here the function is that if you have an interface, then the level set function phi is defined that it is positive in phase 1 and negative in another phase. So that means this interface is the value of phi is 0 at the interface. Okay, so this function is advected. You will have the similar kind of equation to advect this dou by dou t of phi plus v dot grad phi is equal to 0. That is how you advect this. Now, because this P does not represent the volume fraction, then it needs to be related with volume fraction. So one can have this alpha represented in terms of, say, if it is negative, then this value. If it is positive, then this value. But in order to take care of the discontinuity at the interface, this is smooth over few cells, so this can be done using this expression. Another problem with this method or level set is that it needs to the interface will not remain or will not be inherently conserving. The mass of the phases on the both sides of the interface may not remain same. So the value of phi needs to be reinitialized after few time steps. But the advantage of level set method is that it gives you a good normal to the interface. The normal to the interface calculations are accurate. As a result, your surface tension calculations will be accurate, and you can minimize the parasitic currents we just discussed. Okay, so that is in short level set method. Now, if to summarize, so we have talked about volume of fluid. First, we talked about what are multi-phase flows and what kind of approaches one is, one can use interface capturing method, or one can use averaging method, say Euler or Euler-Lagrangian method. Interface capturing methods should be used when there are bubbles, when you don't have many number of bubbles or many number of droplets, or the interface can be resolved, right? And then there are number of issues. So when one needs to model contact line, or so when there are three-phase contacts, then one need to take care of it. There may be a dynamic contact angle. When the films are thin, then it becomes a problem. And when you have heat and mass transfer, then you need to capture the thin boundary layers at the interface, and phase change modeling. So those are some of the challenges associated with it. Okay, so there are some questions. Sir, do we need to consider van der Waals forces between interfaces? It's fluid interface, so van der Waals forces are there, I think. So yeah, van der Waals forces will be there, but when we talk about at the continuum level, we don't need to take into account the van der Waals forces. But if you are coupling it with bigescopic flows, then you might need to take into account. So to answer your question, what we have been doing or what we have been discussing, we don't need to take into account the van der Waals forces in the continuum assumption. Yeah, so now I can take up other questions if there are. If the dispersed phase size is very small, how to decide mesh size? So typically you can decide that whatever is your size, to capture that bubble, you will need at least 15 elements. I will suggest 20, but at least 15 elements should be required to model. And typically you use structured mesh to model dispersed phase. Another question is, can you mention some comprehensive sources with regard to VOF and level set methods? It is vast topic. So there is a book by Professor Tryggvason and Professor Stephen Jalaski, which is for multi-phase flow methods. So I think that is one of the sources, or you can read number of review papers that are available on the topic. Yeah.
Sir, as you have told that in VOF method, the interface is a little bit uncertain. And when we use the level set method, it does not conserve the mass continuity equation. So there are some errors in this. So that's why the people have used combined level set and VOF method. So I wanted to ask that how do we couple the VOF and level set method? What are the equations we will need to consider?
So you will consider then, say you need, if you are doing VOF as well as level set, then you need to solve the volume fraction equation as well as level set equation. But you will use, so you will need to have a coordination between alpha and the phi. You are reinitializing phi after every time, and you are using phi for what it is good for. It is good for calculation of volume fraction, right? And you are using alpha for mass conservation. I think there are a couple of papers on method called CLS VOF, so you can refer to them for details.
Okay, sir.
So there's someone who is asking, hello sir, how to get uniform size distribution and how to control aggregation in state tank in a oil in water emulsion. Okay, so I don't think this is related to modeling, but probably it is a general question on multi-phase flow. So how to control aggregation in a straight tank in oil and water emulsion. I think if you are using a stirrer, then probably you are anyway avoiding or anyway removing the aggregation. Generally, it will not tend to aggregate if your stirrer size is high. I think, does that answer your question?
Sir, in your previous slides, in level set method, you showed that alpha in the form of phi.
Yeah.
So while combining level set method and VOF method, do we use that alpha so that to combine both phi and to combine both equations to get a
No,
combined level set?
we will not necessarily use that alpha. I don't remember exactly what is used in coupling those, but I don't think that you will use that alpha for combining the two, because you are solving volume of fluid method already, and then you are using this level set method to identify the interface. So I think it has to be connected with how you reconstruct the grid.
Okay, sir.
So how people have used it, that needs to be looked into. But I think from alpha, one will calculate phi probably.
Sir, so can you please explain again the that slide in level set method where you have
So it is not about what I am talking about is, if you look at this, phi is either positive or negative, and we will need volume fraction for say calculation of bulk properties, density and viscosity and so on. So we will need value of alpha. So alpha is 0. The thing is that the interface, if you take a discontinuity, then everything will be very problematic, because density, say for example, 1 to 1000 will be changing, and then you have a lot of discontinuity there. So you will need to change this. It will not be a sharp change. The change will not be sharp, but rather a continuous change, right? Like this. So in order that you are changing your alpha, if you just take that 0 and 1, that will be a sharp change. If this change is happening between the two cells of alpha over few cells, then you have, say, this is delta x, or C delta x is this thickness. So on one side you have, say if it is negative, then you have 0, fine. If on other side you have positive, then this is 1. And in between, how this is changing, you are calculating alpha from here. So that is to maintain or to smoothly change the properties over the interface.
Sir, you have taken C is equals to C is equals to 3, you have taken, sir. I think
Yeah,
at the bottom
so
of the
that is a model parameter. How sharp you want to have this interface. That is a numerical parameter. So C is
Okay, sir. Yeah. Thank you, sir.
Sir, what sort of turbulence model should we use, like based on a given problem? What things we should consider? And what
Yeah.
are the important like CFL number or anything parameter that we should consider for the mesh size?
Of course, you will need to take into account CFL number, but also, so CFL number is for convection. Here, you will also need to take into account, say, the time constant or the time from the surface tension perspective, from the diffusion perspective. So diffusion perspective, you consider even in other cases, but here you will need to take into account the time constant from the perspective of surface tension also. Yeah. So somebody had suggested that the Professor Biswas and Professor Gaurav Tomar's paper is for CLS-VF method. You can look at the paper by then.
Can we use adaptive mesh refinement to get the interface correctly, or is there a problem in using that?
You can use adaptive mesh refinement. So because that will be helpful if you want to so if you don't want to use refined grid, so it will help you in reducing the grid size. But the problem there is that it's the adaptive mesh refinement should be dynamic, except in the cases where you know that your bubble or droplet is going to be stationary, because you want one of the things that you want the interface should be sharp. For that, you need the refined mesh near the interface, right? So you would want that, but then if it is moving, then you will need to make sure that the refinement is continuously happening and there is no change in the grid size at the interface. Otherwise, it might be a problem.
Sir, usually which type of turbulence models we are using, like depending on the problem application?
You can use the similar turbulence models that you use for your single phase flow, but you will need to, and the same kind of turbulent, same kind of facts that need to be taken into account. For example, you can use K epsilon model in free surface conditions and K omega model. But at the same time, you also need to take into account the interaction of the interface with the surface with your interface. So some terms may need to be included in your turbulence models, that how because the interface may for example, if there is turbulence in the gas phase, then the liquid interface may act as a source of dissipation of the turbulent kinetic energy. I have not modeled those, I have not done work on it, so I don't know exactly what models will be good, but this is something that one needs to take care.
Thank you, sir.
Okay, so any more questions for Professor Raghavendra? So with this, we can end the theory session here. Professor Raghavendra, thank you so much for this wonderful session. Yeah, and Professor Raghavendra is our esteemed faculty partner of Open Foam team FOSSEE, and he has helped us with guidance and such sessions during workshop earlier also. So the FOSSEE team is grateful to you. Thank you so much for joining.
Thank you.